everybody. Welcome back to Measure Theoretic Probability. In the previous video, we defined what it is to have a limit of a sequence of sets. And if you take sets A1, A2, A3 from a sigma field F, then the limit of the sequence, if it exists, is defined in terms of unions and intersections and is again in F, which means we can take the probability measure of the limit because F is the collection of measurable sets when you have a given probability space. And in this video, I want to compare the probability measure of a limit of a sequence of sets, which is another set, to a limit of probability measures of individual sets. So let's get right into it. I have a probability space, a non-empty set omega, a sigma field curly F, and a probability measure P. Let's take sets A1, A2, A3, etc. from the sigma field F. We defined last time the limit infimum or lim-inf of this sequence to be the union as n goes from 1 to infinity of the intersection as m goes from n to infinity of the am. So we're unioning these tail intersections. And we get another set in F, so it does make sense to talk about the probability measure of this lim-inf set. We also defined the limit supremum or lim sup to be the intersection as n goes from 1 to infinity of the union as m goes from n to infinity of the am. Again, this is going to be a set in the sigma field, which is closed under countable unions and intersections. And if these two sets are equal, that is how we define the limit of the sequence. And if they're not equal, then the sequence doesn't have a limit. You certainly have seen sequences of numbers that don't have limits, and that could happen with sets as well. Now, as we just noted, all of these sets are defined using unions and intersections of sets in the sigma field. And because a sigma field is closed under countable unions and countable intersections, the lim-inf, the lim sup, and the limit, if it exists, are new sets in F. And so it does make sense to talk about the probability measure of each because the sets in F are precisely the sets for which that probability measure is defined. Now, on the other hand, if we look at the probability measure of each individual set, so P of A1, P of A2, P of A3, this is just a sequence of numbers between 0 and 1, but numbers. And this sequence may or may not have a limit. So we can talk about the limit as n goes to infinity of the probability measure of the an if it exists. And if it exists, my question to you for today is how, if it does at all, how does it relate to the probability measure of the limit? So we're going from a limit outside a probability measure to inside or vice versa. If you have a continuous function f and you take a sequence of numbers x1, x2, x3, etc., if you take the limit of that sequence, if it exists, and plug that into f, if f is continuous, you will get the same thing as taking f of the individual x's and taking the limit of those. That is a property of continuous functions, and that is the reason that this theorem I'm about to state is known as the continuity of probabilities theorem. So in the future, if you're using the results of this theorem within some bigger proof, then you should cite continuity of probabilities. You would say, by continuity of probabilities, I have this result. And what are those results? There's two parts to this theorem. There's an I and double I. And I says if we have an increasing sequence of sets, an increasing to a, so you'll recall that means that A1 is contained in A2, is contained in A3, and they're increasing out to a union. In this case, the limit of the individual probabilities is equal to the probability of A. Now, A here is the limit. So we are in fact saying the limit of the probabilities is the probability of the limit set. I'm sure you know what's coming in part 2. If we have a decreasing sequence of sets, we have an A1 that contains an A2, that contains an A3, and they're approaching an intersection, then the limit of the individual probabilities is the probability of A, which is the limit of the individual A's. So again, we have a limit outside is equal to a limit inside. So this is our first theorem. These are two conditions for which we can pull limits inside and outside of probabilities. And again, if you ever use this in your work, you would cite, by continuity of probabilities, I can do this. Let's prove the first part of this theorem. Suppose we have a sequence of sets an increasing to a set A, and A is necessarily the union of the ANs. So I've got like an A1, an A2, an A3 looking something like this. We're going to pull a very standard trick now. It's standard to us now at this point in this series. I'm going to rewrite this union as a disjoint union because these sets are clearly not disjoint. A1 is contained in A2 and so on. But I'm going to take B1 to be this part here, A1. I'm going to take B2 to be this ring out here, which is everything that's in A2 and not in A1. So I've written that as A2 intersect the complement of A1, but we can write that with that backslash, that set minus notation, if we want to. I'm going to let B3 be everything that's in A3 and outside of A1 and A2, etc. And so if I union all of these ANs, or not all of them, so if I union like A1, A2, A3 up to a fixed AN, I just get the fixed AN because of this containment. And if I union the rings, the B1, that core, and then the B2 ring and the B3 ring up to the BN ring, I will get the same set, which is going to be AN. So what we've done is rewritten our limit set, our A, which is a union of the ANs, as a union of disjoint sets. And furthermore, we have that if you take just a finite union of the BNs up to, say, M, you will get the set AM. Rewriting a union as a disjoint union, I feel some countable additivity coming on. Let's try it. The probability measure of the set A, which is a limit of the ANs. So if you replace this A with the limit of the ANs, you'll really see that limit inside, and then by the end of this slide, becoming the limit outside. The probability measure of A is equal to the probability measure of the union of the ANs, which is equal to the probability measure of the union of all of the BNs. But the BNs are disjoint and P is a probability measure. So by countable additivity, I can pull this union out and rewrite this as a sum of individual probabilities. Now, this is an infinite sum. And when you first learn about infinite sums, maybe in Calc 1 or something like that, you learn about finite sums and then letting that finite number increase and go off to infinity. So this infinite sum is defined to be the limit as m goes to infinity of the sum as n goes from 1 to m of the probability measure of Bm. Now we can use countable additivity again to pull this sum back in because these b's are disjoint. This sum of the probabilities of the bn's as n goes from 1 to m is equal to the probability measure of the union as n goes from 1 to m of the bn's. But this is unioning up those rings to a point. This union up to m is one way to define A sub m. So we get that this is equal to the limit as m goes to infinity of the probability measure of A sub m. We can replace all of these m's right here with n's. It doesn't matter. But what we have shown is the probability measure of the limit is equal to the limit of the probability measures. And that's exactly what we wanted to see. For part 2 of this continuity of probabilities theorem, we want to show this similar result for a decreasing sequence of sets. So we have an A1, and it contains an A2, and it contains an A3, and so on. And they are approaching a limit, which is the intersection. I would encourage you, if you have any spare time, to try to write up a proof similar to the proof we just did in the increasing case. Instead of doing that here, I am going to just use the proof of the increasing case by looking at complements. So if I have an A1 containing an A2, then everything that's outside of A2 is more than everything that's outside of A1. In other words, imagine an A1 and an A2 and think about the complements. The complement of A1 is contained in the complement of A2. And in general, if we have a sequence of sets decreasing like this, then the complements form an increasing sequence of sets. And if I apply the complement to this set A and use De Morgan's laws, the complement of this intersection is the union of the individual complements. So what we have is taking the complement all the way across, we can rewrite this decreasing sequence and its limit as an increasing sequence and its limit. In other words, the AN complement are increasing to A complement. So now we can just use part 1 of the theorem, and we know that the limit of the probability measures of the AN complement is equal to the probability measure of AN complement. We're almost done. We just have to do a little bit of cleaning up here. I'm going to rewrite the complement probabilities as 1 minus the non-complemented probabilities and move things around. And this gives us exactly what we want, which is the limit as n goes to infinity of the probability of AN is equal to the probability of A for the decreasing sequence of sets. So we have finished proving the continuity of probabilities theorem. That wasn't bad at all. And this is such an important theorem in measure theory. You're going to be citing this one a lot. Not every sequence of sets is increasing or decreasing. Often we can rewrite them in a way that we're dealing with sets that are increasing or decreasing. But I would like to get to a limit of a sequence of sets if it exists, the probability measure of that limit being the limit of the probability measures without having to go through increasing or decreasing sets. In other words, I would like to say that the probability measure of the limit of the ANs is equal to the limit of the probability measure of the ANs, but not start with increasing or decreasing sets. I have a theorem for you, and we will get to that result in part 2 of this theorem. But for part 1, I'm going to start with any sequence A1, A2, A3, etc. in the sigma field. And the result here is that the probability measure of the lim-inf of that sequence is less than or equal to the lim-inf of the probability measure of that sequence is less than or equal to the lim-sup of the probability measure of that sequence is less than or equal to the probability measure of the lim-sup set. And once we prove that, we will easily be able to prove the result that if the limit of a sequence of sets AN is equal to a set A, if it exists, not necessarily from increasing or decreasing sets, then the limit of the probability measures is the probability measure of the limit. Again, A is a limit set. So this is like a limit outside becoming a limit inside. In short, I'm going to write AN approaches A is going to imply that the probability measure of AN approaches the probability measure of A. Let's prove part I. Okay, so let's start off with the left-hand side. I'm going to write down the probability of the lim-inf of the ANs, and the first thing I'm going to do is just write out the definition of the lim-inf as a union of an intersection of sets. I'm going to take this intersection as m goes from n to infinity and define this to be a set that I'm going to call B sub n. Now, note that if you intersect A1 through A infinity, you likely do not have a lot in common with so many sets. So that's going to be kind of, doesn't have to be, but just heuristically, it's going to be kind of small. And if you knock out one of those sets, the rest of them are more likely to have something in common. So that's going to be a little bit bigger and containing the first full intersection and so on. So what I'm trying to say is note that the BNs here are increasing. They're increasing, and if you have an increasing sequence of sets, they increase to the union. So I'm going to define B to be the limit of the BNs, which is going to be the union of the individual BNs. Well, here is the union of the individual BNs. So this whole expression is equal to the probability measure of B. The BNs are increasing to B. And so by the continuity of probabilities theorem, part I to be exact, this probability of this limit of sets is equal to the limit of the individual probabilities. I'm just going to plug in what Bn was. It's defined in terms of an intersection. So this is the limit of the probability of an intersection as m goes from n to infinity of A sub m. This limit definitely exists because it's an increasing sequence. And so it does make sense to have this limit here. And if the limit exists, that means that the lim-inf and the lim-sup were the same, and the common value was defined to be the limit. So I can just sort of trivially rewrite the limit as the lim-inf. I can't go the other way. If I have a lim-inf, I don't know it's a limit until I compare it to a lim-sup. But if I have a limit, it must be equal to the lim-inf and the lim-sup. So I choose, because I'm looking at what I want to prove, we're going for that first inequality in that big sequence of inequalities in this theorem. I choose to rewrite the limit as the limit infimum of the same probability. And note that this is an intersection of an plus 1, an plus 2, and the intersection of a bunch of sets is going to be contained in any one of them. In particular, the intersection of an plus 1, an plus 2 must be contained in an and an plus 1 and an plus 2, but this is really all I care about. I'm going to use monotonicity of the probability measure to say that the probability measure of this set is less than or equal to the probability measure of this set. And from here to here, that is the first inequality that we wanted to prove in this theorem, part I. Let me remind you again of that theorem. We have just proven this part. I now want to prove this part, which maybe you don't need to be here for this because this part has nothing to do with probability. I have here a lim-inf of a sequence of numbers, and it's less than or equal to a lim-sup of a sequence of numbers. No one cares about probability here. So I'd like to show, or maybe you already know this, so move along, that the lim-inf of a sequence of numbers is less than or equal to the lim-sup of the sequence. Because it's not going to take that long, I just decided to throw it in here. Suppose we're looking at the limit infimum of a sequence of numbers, A1, A2, these are little a's, these are real numbers. We can define this as a supremum of an infimum, but we can also define it, if you remember that funnel picture, We kept taking infimums and chopping numbers off and taking a limit. And so this is, in one way, this is defined is the limit as n goes to infinity of the infimum over all m greater than or equal to n of the am. So this is like a minimum of all of an plus 1, an plus 2. And that minimum is certainly going to be less than or equal to a maximum. So I can say that this infimum, this real number right here, is less than or equal to the supremum of the same sequence. But I can unravel the definition of a lim sup of a sequence of numbers. This is defined to be the limit supremum of the ans. So what we've shown here in general is that the lim inf of a sequence of numbers is less than or equal to the lim sup of the sequence. And to go back up to this theorem, no one cares that these are probabilities. This is just a lim inf of a sequence and a lim sup of a sequence. So we have proved this inequality. It's time to go for the last inequality. I want to kind of mimic what I did in the first inequality, where I started with this and I got to this. So I'm actually going to start on this right side. I'm going to start with the probability measure of the lim sup set. I'm going to write out the definition of this lim sup set as an intersection of a union, and I'm going to define B sub n to be this union, this partial union. So if I'm unioning A1, A2, A3, I'm unioning a lot of things. That's a kind of large set. And if I knock out A1, that's a smaller set contained in the first set. So what I have is a decreasing sequence of sets, B1, B2, B3, decreasing to, when you have a decreasing sequence, they decrease to the intersection. So I'm going to call that B. B is defined as the full intersection of all of these sets. And these dots before an equal sign means that this is a definition here. We're defining B to be this intersection. So here I have an intersection of some BNs, and we're defining that to be B. So this whole thing becomes the probability measure of B. And because the BNs are decreasing to B, by continuity of probabilities, by that theorem, part double I, we can say that this probability measure of this limit is equal to the limit of the individual probability measures. So now I'm going to rewrite the Bn as the union it is of the AMs as m goes from n to infinity. This is simply how we define Bn. And the limit existing means that a lim inf and lim sup existed and were equal. And I'm in the lim sup portion of this proof. I am going to choose to rewrite this limit as the lim sup of the same sequence. Now, this is a union of an plus 1, an plus 2, and that is going to be potentially larger than larger than any one of them. In other words, this union set is going to contain an. It's going to contain an plus 1 as well and other sets, but this is what I care about. It contains an. So I'm going to use monotonicity of probabilities again. The probability measure of this sort of bigger set is greater than or equal to the probability measure of this smaller set that's contained within the bigger set. And from this side to this side, this is what we wanted to show. That is the final result in the 4 terms and the 3 inequalities that we wanted to show for this theorem, part I. Part double I of this theorem states that if the ANs are converging to a set A, not necessarily increasing or decreasing, then the probability measures of the individual sets are converging to the probability measure of the limits. So limit outside becomes a limit inside. To prove this is actually quite easy given we have done the work in part I. Recall that we have the probability measure of the lim inf less than or equal to the lim inf of the probability measures less than or equal to the lim sup of the probability measures less than or equal to the probability measure of the lim sup. This theorem is starting with the assumption that the limit of the ANs exist. So the lim inf is simply the limit of the ANs. If the limit exists, again, it has to be the common value of the lim inf and lim sup, and they're necessarily common if the limit is assumed to exist. So this is the limit of the ANs, which we're calling A, and so is this. I have a big inequality here. I've got the probability measure of A on both sides, which squeezes these guys in between them. They must be the same number. And if the lim inf and the lim sup of a sequence are the same, then that's how you define the limit. So both of these must be equal, and they must be equal to the limit as n goes to infinity of the probability measure of the AN. To recap, what we've just written is the probability measure of A is less than or equal to the limit as n goes to infinity of the probability measure of AN is less than or equal to the limit again. So obviously this is actually equal. And because this is all less than or equal to the probability measure of A, this stuff is like a squeeze theorem here. The limit inside has to equal these boundaries. This number can't be greater than or equal to something and less than or equal to something unless it's actually equal to that something. And this is what we wanted to show. So we have finished our proof of part 2 of this theorem. So many times already in this course, we've had inequalities that turn out to hold in both directions, which means we have equality. When I see an inequality like this in analysis or measure theory, the first thing that comes to my mind is, are there examples where these inequalities are strict, or really are these going to turn out to be equalities? Well, in this case, we do have examples, and I'm going to give you one for the inequality all the way over here, and you can maybe adapt it or look at it for the other inequalities in this statement up here. I am going to consider two disjoint sets, A and B. I'm going to assume they both have positive probability measure that is strictly less than 1. I'm going to let little p be the probability measure of A, and I'm going to let little q be the probability measure of B, and I'm going to assume that 0 is less than p is less than q is less than 1. So if you can come up with sets that satisfy this, then this is going to give us an example of, I claim, a strict inequality right here. I don't have a sequence though yet, so I'm going to define a sequence AN to be alternating A and B. AN is going to be the set A if n is odd, and the set B if n is even. Remember, these sets are disjoint. They both have positive probability measures. The probability measure of A is strictly less than the probability measure of B, and they're both strictly less than 1. Let's look at the lim-inf of the probabilities of the AN. Now, AN is A, then it's B, then it's A, then it's B, and it's just alternating. And those probabilities are P and Q and P and Q and P and Q. So if you're looking at that sequence of probabilities, it looks kind of like this. Remember how we define the lim-inf? We look at the inf or the infimum or the minimum of all of these, and that is P. And we chop off the first one and we look at the infimum of all of these, and that is still P. And we chop off the first two and we look at the infimum of all of these, and that's still P. And we create a sequence that we take the limit of, and that's how we define the limit infimum. Well, that sequence we're taking the limit of is P, 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 P. So this limit is P. So that takes care of the lim-inf outside of the probability measure. Let's take the probability measure of the lim-inf. So continuing with this funky sequence, let's look at the lim-inf of the ANs. That's defined to be a union of an intersection of the ANs. Check out this intersection. This is going to be a sequence of A's and B's. It may start with B, it may start with A, but ultimately it's an A intersect B, intersect A, intersect B, and the A's and B's were defined to be disjoint. So this intersection is the empty set. And when you union the empty sets, you just get an empty set. And the probability measure of an empty set is always 0. So here I've got a lim-inf of probabilities, which is P, which by design was strictly greater than 0, and a probability of a lim-inf that's equal to 0. And so not equal to P, strictly less than P. And this is an example of strict inequality in the first inequality of the lim-inf lim-sup stuff from the last theorem, part I. So if you'd like to, you can play with the other side of this. Again, look at all of the inequalities. There are 3 inequalities. There were 4 terms in the last theorem, part I. And this is actually an example where all of those inequalities are strict. We are moving ever closer to something I brought up a few videos ago. I was a little premature in bringing that up. And that is the famed Borel-Cantelli lemmas. There's a Borel-Cantelli lemma 1 and a Borel-Cantelli lemma 2, and we're ready to state and prove the first one, but I'm saving it until we're ready for the second one. Now, the second Borel-Cantelli lemma involves independence of events or sets in a sigma field, and we haven't defined that yet. So I'm just going to take the rest of this video to just get a jump start on independence, and maybe we'll get to Borel-Cantelli next. At worst, in 2 videos. So a little bit about independence. Now, before measure theory, if you had events or sets A and B, they were independent if the probability measure of the intersection is equal to the probability measure of the individual sets multiplied. My preferred definition for independence is an equivalent definition involving conditional probability. The probability measure of A given B, if they're independent, should just be the probability measure of A. No one should care that you've been given B. And because this conditional probability is an intersection probability over the probability for B, then this is going to be the product of the individual probabilities. And so you can see that these two definitions of independence are equivalent as long as we don't have a zero in the denominator. So again, this is my preferred definition of independence because I think it makes more intuitive sense. Given you have this information, what happens over here? Nothing. Nothing different, at least. But we're not going to use this or talk about this or come up with an analog for this because we don't know anything about conditional probability yet in this course. So let's stick with this definition and have an analogous definition in measure theory. I'm going to start with a probability space, an omega, an F, and a P. I'm going to let A1, A2, A3 on up be a collection of sets from F. I'm not talking about sequences here, so the ordering is not important. I just have numbered a bunch of sets from F. We say that A1, A2 up through a fixed AN are independent, or more specifically, mutually independent, if for any J from 2 to N and any indices K1, K2 up through a Kj that are ordered and between 1 and N inclusive, if the probability measure of this intersection is equal to the product of the individual probability measures. In other words, this multiplication, this intersection becoming a multiplication of probabilities has to hold for every pair of sets and every triple of sets and every quadruple of sets and so on. This is the definition of independence of sets, or more specifically, mutual independence, not to be confused with pairwise independence that I'm going to come back to in a moment. But first, I want to define independence of sets if you have a bigger collection of sets, so not finite, countable or even uncountable. If you have an infinite collection of sets that's countable or even uncountable from a sigma field F, they are defined, the sets in that collection are defined to be independent if every finite subcollection of sets or events is independent in the sense of our previous definition. I'll say more about that later when we actually need it. Let's get back to the idea that mutual independence does not imply pairwise independence. Quick example, just going to flip a coin twice. The outcomes are heads, 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 tails, tails, heads, or tails, tails. So that is the sample space. I'm going to define 3 events or sets, A, B, and C, as follows. So if you want to give these event definitions, A is going to be the event I get heads on the first toss, B is going to be the event I get heads on the second toss, and C is going to be the event that the 2 tosses give the same result. In all cases, all pairs intersecting here, all pairs have one common element, and that is heads, heads. So it's easy to see, and I am kind of blowing through writing this out because this is just, your probability 101. Let me know in the comments if you're having trouble following this, and I will expand upon this. But the probability measure of the set A, because it has 2 out of the 4 equally likely outcomes, is 1/2. The probability measure of the set B, also having 2 out of 4 of the equally likely outcomes, is 1/2. And it is also 1/2 for the probability measure of C. I'm going to start intersecting these. And as I was just saying, if you intersect any 2 of these, you get heads, heads every time. So for example, the probability measure of A intersect B is the probability measure of the singleton set containing the one outcome heads, heads in our 2-flip experiment. And that outcome has probability 1/4. And you're going to get the same thing if you look at the probability measure of A intersected with C or B intersected with C. Now, 1/4 is 1/2 times 1/2, and all the individual probability measures were 1/2. So what we have is the probability measure of any of these pairwise intersections is in fact equal to the product of the 2 probabilities, which is looking like we have independence. And in fact, we do have independence of A and B, of A and C, and B and C. But this is supposed to be an example of pairwise independence, not implying the mutual or non-pairwise independence, what you would get if you just say independence of all of these sets. The probability measure of A intersected with B intersected with C, if you intersect all of these, you get the common value, the single output that is the result of 2 coin flips, the heads, heads. The probability measure here is 1/4, while the probability measure for each individual set was 1/2. 1/4 does not equal 1/2 times 1/2 times 1/2, and therefore the probability measure of this intersection is not the product of the individual probability measures. So while these sets, A, B, and C, are pairwise independent, they are not mutually independent or independent if you leave off the word mutually. So be careful. The main point of today's video was to talk about continuity of probabilities and some cases where you can take limits inside and outside of the probability function that is defined on sets in the sigma field. We then, for the purpose of forward momentum, talked about independence a little bit in this video, and we talked about how a collection of sets could be independent, meaning that, all pairs, all triples, all quadruples, intersecting all of them, when you compute the probability of an intersection, you have to get the product of the individual probabilities. In the next video, I'm going to start with a collection of independent sets. We just defined that. And I'm going to create the sigma field generated by that collection of independent sets. So the sigma field is a bigger collection of sets. Are the sets in the bigger sigma field still independent? You'll have to come back to find out.